So why we need this audio video compression? It is the same, like other data. For example, image compression. It reduces the storage space, and it reduces the bandwidth requirements, and definitely the overall communication cost become lower, and it also enables us to have the new applications. So that's the very same reasons that we do any sorts of compression. So similar things goes for audio and video compressions. So now let's look, what we mean by audio compression and what is the basic idea behind it. So there are two, kinds of, broad categories of audio compression. One is predictive encoding and another is perceptual encoding. Now, predictive encoding is, very simple, that, it just encode the difference between the samples instead of the sample data. So I'll give you an example what we mean by the difference between the samples, right? You see, we encode the difference between the samples, not every sample data. So we will, for example, let's say we have one sample data, now the second data, the third data, the fourth data, and what we do is just, we just have the difference between these two and the difference between these two and the difference between these two. So and then we apply coding scheme on their difference values, not directly, sample by sample. And perceptual encoding is, we'll achieve the audio compression, if we just, analyze that how our own auditory system, auditory systems means how we listen the sound in our by our ear, right? So the human system has some limitation. So what we will do, we'll exploit that, limitations to have the better compressions of audio. Now it is the same like, image compression. If you remember the image compression, there are some limitation on human eye, and we took that advantages to compress the image. So same things we do, that first we analyze that how our, auditory system works, how we listen our sound, and then based on that we just, come up with some new techniques. So that's why that is called perceptual encoding. That depends on our perception. And predictive encoding is, it just, mathematical steps. So how we do the, predictive encoding? So one example is, differential pulse code modulation. Now how the differential pulse code modulation reduces the bit rate or reduces the audio size is like that. It sends the difference between the samples. Now I mean, what is the benefit if they send the difference between the sample, how it reduces the bit rate? So let's see that. If you remember that, quantization error, when some, we do some quantizations, the maximum quantization error happens, that is step size by 2. If you remember, if you don't remember, please go and check that when we studied, audio signals, those things. So anyways, step size by 2 is the maximum quantization error. And how we calculate the step size? So calculation of the step size is very simple. We first, have the differences, the range of input voltage. So range of input voltage means, V max minus V mean, and then we just divide by the number of steps or number of quantization level. And sometimes this quantization level we represent in this manner, power of 2. And so in that case we say this n is, bits per sample. If you just quickly remember that, for examples here, let's say something like that. Let's say our analog voltage is something like in this range. So it is, let's say, V minimum, and that's the V maximum. So what we do is, this is the voltage range. The voltage range is V max minus V mean, and then how many levels, we like to have, right? How many levels we like to have? Let's say if we have L levels, let's 16 levels. So that means how many bits we need for to represent these samples, to store these samples, is 2 to the power, 4 equal to 16. So that means we need 4 bits, we need 4 bits to represent each sample, right? To identify each level. So, and the 4 bits means 0 0 0 0. This is level, one level, and then if we go in this way, this is another level, right? If you remember that one. So anyway, so the n is basically number of bits per sample. And if you remember that, that if we increase this n, so that means we are increasing this, number of levels. Ultimately, if we increase this, number of bits, 5 bits, maybe 6 bits, 7 bits, so that will actually increase the data storage requirement or data rate. So and this L also. So in another word, let's say, what is our ultimate target, ultimate aim? Our ultimate aim is, we try to, minimize the quantization error as much as possible. Now, to reduce this quantization error, so definitely, this quantization error is, step size by 2. So that's in turn depends on this L. So that means this L should be increased. So to reduce the quantization error, so number of levels should be increased so that step size decrease and then quantization error decrease. So to increase this, number of levels, definitely we need, to increase this n. So increasing n means what? Increasing n means number of bits per sample. That means this bit should be increased. But as you know that if we increase this bit, so that means for each sample we increase the number of bits. So that means the storage capacity will be increased, bandwidth will be high. So that's a problem. So what we do is this DPCM, what it does is basically reduces this input voltage range. If it reduces the input voltage range, ultimately, so the step size will be reduced and the quantization error will be reduced. So still, without changing L and N, we can still, reduce the quantization error. So that's the idea why. And I mean, we can reduce the quantization error, or we can say that we can, reduces the bit rate. So how is that? Because if you remember that if we decrease this range, this input range, if we decrease this input range, so if we have same number of levels still, so that means what? Because this is already reduced, so that's why it needs, the less quantization error. So that means, so we don't increase this n. Because we don't increase the n, so we don't increase the storage. So that's the idea. So how we do that? That's an example. So this is an example of, DPCM. Let's say our original signal sample values is, let's say, first sample value is 1, the next is 3, and then 6, 7, and 9. So just, a tiny example. So what is the input voltage range or input, data values range? So the maximum is 9 and the minimum is 1. So range is 8. So, but if we apply DPCM encoding scheme, so what is the encoded data then? The encoded data is very simple. The very first sample we keep as it is. So that is 1. And the second sample is, it would be the difference between this one. The second is 3, but we will have the difference, between this one and the previous one. So 3 minus 1 is 2. And then 6 minus 3 is 3. And then 7 minus 6 is 1. And then 9 minus 7 is 2. So now the encoded, signal is 1, 2, 3, 1, 2. It is not 1, 3, 6, 7, 9 anymore. So that's why input range now become, the maximum is 3, the minimum is 1. So input range become 2. And before encoding, the input range was 8. Because we decrease the input range, so definitely, we can have better, compression, because, we don't need to increase the quantization error with the same quantization, reduced quantization error. And so we can still, send the same information bits. Or in another word, we can increase, we can keep the quantization error same, and by having the same quantization error, we can basically, adjust more data rate, because we can store more level here, right? Less level here. So the decoded signal sample is how we decode the signal, how we decode the signal. Let's say we transmit 1, 2, 3, 1 and 2. So how we can decode? The first sample keep as it is 1, and we know the second sample would be the addition with the previous one, because it was the subtraction, we subtracted, right? So now we will add up. So this 2 plus 1 equal 3. And now the next sample is 3, and we will add this 3. So 3 plus 3 is 6. Now this 6, and we will add this 1, that is 7. And this 7 we will add this 2, that is 9. So exactly same. 1, 3, 6, 7, 9. It is the same, 1, 3, 6, 7, 9. So ultimately what we did is the range of input voltage is reduced. So step size is reduced without increasing the number of bits per sample. So this DPCM example, please you practice. I can give this sort of example in your exam. Now what is perceptual encoding, how it works? Perceptual encoding is so that things is basically one sort of, if you remember that we told is kind of, you know predictive encoding, because in predictive encoding, we just try to predict, right, based on first we encode, as a subtractive manner, and then we predict like these sort of things. That's why it is called predictive encoding. It is solely mathematical. Now we go for perceptual encoding. The perceptual encoding, there are different kinds of phenomena. One is temporal masking, and another is frequency masking. Now what is that, temporal masking and frequency masking? Sometimes, think about that. You are just, at a stage performance, you are enjoying some stage show, stage performance, something like that. And what happens sometimes, it sometimes, very big sound comes, suddenly a very louder sound, a very very big sound, a loud sound comes. So at that time what happens, the very momentarily, for a small moment, after listening a very large sound, after listening a very large sound, just for a millisecond, we don't listen anything, so you can say that our auditory systems, our ear becomes, insensitive. So why that things happen? That's because of temporal masking. Okay, so this is a phenomena. This is kind of, incident that naturally happens. That's called temporal masking. Also, many times what happens, we don't listen some sort of, high frequency sound, or maybe not low frequency sound. For examples, they who constantly works, in some musical performance, for example, might be a person that who always, works with the sound board. Sometimes he cannot listen high frequency signal compared to others. Why? That's called frequency masking, because he is very close to a very high frequency signal, and that high frequency signal actually, causes, not to hear some other kind of sound. So that kind of thing is called frequency masking. So whatever, we will, explain more on that. But for this time being, just listen that there are two kind of, phenomenon. One is temporal masking, and one is frequency masking. So because of that things, sometimes our listening pattern changes. So and actually it very much depends on the person. Person is specific. Maybe this person, may perceive, one sound differently, than this person. So this kind of things happen. So first of all, we need to analyze the sound itself. We have a, let's say, sound signal. We have a sound signal. What we need to do, we need to analyze this sound signal in details. And the sound signal or audio, sometimes we say acoustic signal, that we say acoustic, because that's kind of, sound. It is a acoustic. So it's this acoustic signal, we need to analyze from human psychology perspectives. So that means psycho, PSY, let's say maybe CA, so psychology. So let's say psycho. So this psychoacoustic model, the psychoacoustic model of hearing, that is very much important. So whenever we like to have some compression and analyze some sound, we need to analyze from psychoacoustic perspectives, that how our human auditory system works and what sounds we can listen, what not. So based on that result, we can apply some sort of compression things. So to have a deeper understanding, let's first we explain a terminology that's called hearing threshold. And if you remember that, what is hearing threshold? Hearing threshold is the minimum sound level that we need to hear. For example, let's say this person, right? And maybe this person maybe, to listen something, to listen some sound, at least the sound strength should be 0 dB. At least the sound level should be 0 dB. Or maybe this is another person, you know maybe he listen, at least the sound level should be at least 1 dB. Okay, so this is called hearing threshold. I already explained these things, right? So this person will not listen any sound if the sound level below 1 dB. For example, this person will not listen anything if the sound level goes below 0 dB. So that's why this 0 dB, at least to listen something, the sound level should be at least 0 dB for this person, right? And 1 dB for this person. So this 1 dB and this 0 dB is this 0 dB, this 1 dB, sometimes we say hearing threshold, right? So it depends on the person, but it's when we work on algorithm and software, we usually take an average measurement, not just for the specific individuals or a specific person. But the very interesting things is that this hearing threshold very much depends on the frequency of the signal, frequency of the sound signal, frequency frequency of the sound signal. In general, this hearing threshold depends on the frequency of the sound. For example, look, this is a typical characteristics curve. This is a typical kind of hearing threshold for each frequency. For example, look, for example, let's say, I don't know, maybe here, maybe this one, at this point, what is this frequency? This frequency is 1 kilohertz, right? 10 to the power 3 means 1 kilohertz. At this 1 kilohertz, the hearing threshold is this one. What is these values? Is maybe around, I guess, let's say 3 dB, or yeah, 2.5 dB or 3 dB. Okay, maybe this one is kind of 3 dB. So we can say that at 1 kilohertz frequency, the hearing threshold is 3 dB. But how about at this is 1 kilohertz and this is 2 kilohertz. You see, this is 2 kilohertz. At 2 kilohertz, the hearing threshold is 0 dB. So and how about this is 2, 3, 4, 5? At 5 kilohertz is also hearing threshold is 0 dB. And how about maybe I don't know what is this one. This is maybe 10 to the power 4, that means 10 kilohertz, right? 10 to the power 4 means 10 kilohertz. At 10 kilohertz, hearing threshold is 10 dB. It's 10 dB. So in this axis is dB, right? So dB. So as you understand, at different frequency, the hearing threshold is different. So, and definitely our ear, our sound system, our auditory system become most sensitive, generally within this range from 1 kilohertz to, how much this is, I guess 5 kilohertz. This is 1, 2, 3, 4. This is 5 kilohertz. Because within this range, our ear can listen a very small level of sound, generally maybe 3 dB to, I guess, maybe 0 dB. You see, 3 dB to 0 dB, this kind of sound level can listen when the frequency of the signal is from around 1 kilohertz to 5 kilohertz. But as the frequency goes upwards, you see, and as the frequency goes even low ranges, at the time, generally the frequency, this sound, our ear become more insensitive. You see, for example, when 100 hertz, around 100 hertz frequency, this the sound level should be at least 20 dB. Similarly, you see, if we frequencies, let's say maybe uh, 15 kilohertz or 20 kilohertz, at that time sound level should be very high, otherwise we don't listen. And that's why you see, sometimes, most of the times, we don't listen 20 kilohertz signal. Very rare we listen. Generally we listen 0 hertz to 20 kilohertz sound our human systems can perceive. But to listen this kind of sound, we need a very high sound level, very high sound level. But in between, just moderate sound level is okay. And the very sensitive, our eye become very sensitive within this frequency range, because here hearing threshold is very low. Okay, so that means, you see, let's say if a sound, for example, there is a sound, let's say, and that sound frequency is, let's say, 10 kilohertz, and maybe that 10 kilohertz sound, let's say, 9 dB, maybe 8 dB, let's say 8 dB. Okay, this is 8 dB, 8 dB. Okay, this, let's say, 8 dB, this sound level is 8 dB. You see, can we listen this sound? This is, this is 10 kilohertz signal. Let's say we have a sound of 10 kilohertz frequency, and the 8 dB sound level. Okay, 8 dB sound level. Can you listen this sound? See, to listen this sound, this 10 kilohertz, what is our hearing threshold? And why hearing threshold is, see, the 10 dB is our hearing threshold, right? Because at least 10 dB to listen any sound of 10 kilohertz frequency, that sound level should be at least 10 dB. So that means we don't listen that sound. This 8 dB sound we don't listen. But how about if this sound level is 12 dB? If this sound level is this one is a, let's say, 12 dB, definitely we listen, because this crosses the hearing threshold. So it means that any sound level, if that goes below the threshold, so that sound level, that sound we can delete. That has no use, because we don't listen that sound. Okay, so now we understand what we mean by hearing threshold. Now we go back, masking. If you remember that we have two kinds of masking. One is frequency masking and another is temporal masking. Let's first we elaborate frequency masking. Now in frequency masking, what happens, you see, that a loud sound in a frequency range can partially or fully mask another sound in nearby frequency range. So this is the concept. For example, you see that this is a sound. Let's say this is a very large sound. You see, the large sound is around 60 dB, and its frequency range is somewhere around, maybe from here, maybe from here, maybe from here, maybe 500 or 600 hertz to 4 kilohertz. Okay, 4 kilohertz. So this is the range of that sound. Okay, now see, now within that sound, this sound range over the frequency is from 500 hertz to 4 kilohertz. Now 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 within this range, you see, there is another sound, is this one, and whose sound level is around maybe 2 dB or 3 dB. And there is another sound, this sound of frequency is 3 kilohertz, and this sound range is maybe a little more than 0 dB. It is the same sound level, I guess 2 dB or something. Okay, so there is three sound that we are seeing. For example, let's say there are four sound. In fact, the one sound is here, that is at 1 kilohertz. The second sound is, let's say, at 2 kilohertz, and the third is around 3 kilohertz, and the fourth sound is, let's say, around 9 kilohertz. Okay, and what is this dotted line? This is hearing threshold, right? Hearing threshold. Now see, can we listen this sound? We don't, because this sound level is basically below the hearing threshold. So we'll delete this sound. And think about this sound. How about this sound? So how about this sound? Of course, this sound is around 60 dB, or even around 60 dB. Definitely we will listen this sound, because the hearing threshold here is this one, so we will listen this sound. And how about this sound, second, the sound that of 2 kilohertz signal. You see, this also crosses the hearing threshold, because hearing threshold is around 0 dB, but this sound is above the hearing threshold, so we are supposed to listen this sound also. But you see, this sound level is basically less than this sound level here, exactly in this, in at this time, at this frequency, because at this frequency still the big sound exists here, and that range is, that sound level is much more than this one. So in that case, we don't listen this signal, this sound. We are supposed to listen because this is above the threshold, but because there is a larger sound, a very high volume sound in the same frequency, so we don't listen this sound anymore. But how about here? So you see, this sound level, this crosses the threshold level, because threshold is this one, so we are supposed to listen. And also this sound is also the higher level than this one, right? In this one, because at this particular frequency, this greater sound level reduces, the level of that sound is reduces, so we should support, we should hear this sound. So that means, on an average, so if we just see that this one, we will listen this sound, and we will not listen this sound, and we will listen this sound, and we will not listen this sound. So that's why you see, this one is audible tone, and this dotted arrow is inaudible tone. So when we try to compress our audio compression, at that time we can safely delete this one, we can safely delete this one, because that has no use. So we can delete this sound, and in this way we can achieve some compression. Okay. And you see, this frequency range, this range of frequency of a high volume sound, this range of frequency become large, this range become large if this sound goes in the higher frequency range. For example, here is an example. You see, this one, this is a very low frequency range, even though this is a very high volume sound, because this situated, this placed in the low frequency range. However, as you go in the high frequency range, if you see any high volume sound, then this range, there's range of masking, that covers, that disrupts other sound levels, that's become very large. So at that time we can delete a lot of other sound, so we can delete those sounds. And how about the temporal masking? The temporal masking is also a very another kind of very interesting phenomena. Think about that. So here we talked about in frequency domain, so here is the frequency. But now let's think a very particular refer time instant. For example, let's say at this time instant, reference time instant, there is a very large sound here, you see, more than 60 dB. Okay, and this is sound A. And there is after 10 seconds of that sound, it's a 10 second apart, there is another sound B. And then after 20 seconds from this one, so there is another sound, maybe this sound is C. Now see that this sound, of course we will listen, but can we listen this sound? You see, this sound level is around 30 dB, right? But maybe we should listen, but is still the larger sound is still at that time at 10 millisecond, around 10 millisecond, that sound is, the volume is still larger than this one, so we will not listen the sound B. But how about after 20 seconds? After 20 seconds, this larger sound now drops to a level, so at that time this sound, which is the sound B, or let's say sound C, whatever, we will listen this sound after 20 seconds, because at that time this sound level reaches the below this sound level. So in that kind of thing, sound B, we don't listen. So this is kind of time perspectives, that when some larger volume comes, so for a very particular time, maybe after 10 millisecond or 20 millisecond, we don't listen other sound. if that sound level is below this larger sound level at that time. So that's called temporal masking. So definitely, so what happens actually, so that the things that happens is loud sound can numb our ears, right? For some short duration of time, our ear become insensitive for some low volume of sound because of the high volume of sound. Okay, so that's called temporal masking. So when we have a sound signal, what we do, we basically analyze the signal, and we see their temporal behavior. That means this time domain analysis. Also we see their frequency characteristics. So first we see the signal in frequency and frequency domain. So let's say this is the frequency, and this is the sound level. And we also see the time domain, and this is the sound level. So, and based on comparison with our hearing threshold, so based on some psychological psychoacoustic model, then we see that what sound we can delete and what sound we can't. So in this way we can achieve the compression. So for example, mpeg 1, the mpeg means moving picture expert group phase. This mpeg 1, it's basically, this is moving picture expert group. So this is one kind of standard. So they had phase 1, so we say mpeg 1. So mpeg 1, the audio mpeg 1, and it used for both audio video, but we are talking now for the audio. So they have sampling frequency 32 kilohertz, 44.1 kilohertz, and 48 kilohertz. And that time domain signal to frequency domain signal, this can be converted by FFT. So FFT is fast Fourier transform. It is some mathematical technique that you can use to convert a time domain signal to frequency domain signal. And then after we convert, let's say like this is let's our sound wave, and this is a time domain, and you can convert to the frequency domain signal. Let's say this is a frequency, and it's look like that kind of things. And then what we do is we divide this whole signal into some specific band, some number of bands. So that's that total sound level. This is one band, this is another band, this is another band, this is another band. We say this is the frequency bands. Okay, and then we see that what happens to this frequency band, what happens to these frequency bands. If these bands is completely masked by some other frequency, or some in time aspect, so we just delete those bands. So that means we allocate 0 bits, we don't allocate any bits for that. And some bands are very less important. So for that, they are, we can say, partially masked. Not all frequency are masked, but partially covered by other sound signal. So we just allocate a small number of bits. And the frequency bands that are not masked at all, not disturbed by other sound at all, we allocate larger number of bits. So that means no compression we do. So in this way, we delete this one, we partially delete this one, and we keep this one, so we can achieve some compression. So finally, the audio stream is adjustable with 32 kbps to 42 kbps under mpeg 1. Okay, now the similar things, but a very updated version we do in mp3. Now what is mp3? mp3 is mp3 is very interesting name. mp3, this mp basically means mpeg 1 or 2. Okay, phase 1 or phase 2. So this mp coming from mpeg 1. Okay, so that you need to note down. And what is 3? This 3 is basically interesting. In mpeg 1 or mpeg 2, generally in mpeg there are 3 level of compression, 3 different levels of compression. Okay, so the basic is same, the basic model is same, just complexity is different. There's level 1, level 2, and level 3. And as you understand, this is the very basic level, and this is the intermediate level, and this level 3 is the decoding and encoding and decoding. The way encoding decoding way is more complex. The basic model and phenomena principle is same, but it has some various other kinds of stuff. So that's why this is called the M. So this means this MP3, MP means MPEG 1 and 3 means level 3. So that means the most complex decoder we used in MP3. So so MP3 means MP3 is layer 3 of the audio, and MPEG means MPEG phase 1. Okay, so like this. So 3 stand for layer 3 and MP stand for MPEG standard 1. Okay, so MP3, so that means MP3 is a form of audio component of the first phase of MPEG. When you talk about the compression, we give some score that what is the compression and the quality and the bitrate level. So for example, the highest quality is 5, quality 5. So it means you know in audio compression or MPEG compression, MPEG compression with let's audio compression with quality 5, let's say score is 5. So quality 5, it means that almost transparent. That means if we just listen our original sound and the compressed sound, we almost don't differentiate between these two. For example, CD quality audio, that is, we can say that is very transparent quality. But the, let's say quality is 4. So it is also not much different, but there are some differences, compared to the original signal, but it is not annoying. We can still listen well. But if the quality compression quality is 3, so that means it's slightly annoying, but it's still okay. And compression level is 2, it means it's really annoying, that we can our ear become painful. And the 1, if the quality is 1, that means it's very annoying. So but definitely the compression level 5, quality 5 means that compression is not much, but the very annoying, but definitely the compression is huge, compression has been done. So if we just think about that MP3, where it's become MP3 is score between somewhere around 3.6 to 3.8. The MP3 score somewhere around 3.6 to 3.8, it's almost 4, you can say. So that's why very substantial improve compared to MPEG 1 layer 1 and layer 2. So layer 1 layer 2 is score between somewhere 2.1 and 2.6. So there is always definitely trade off between quality and bit rate. If we if we like to have very high compressions, that means a lot of data we can compress in smaller places, so definitely the quality will be degraded, something 1 2 3. But if you like to preserve the quality, so then less compression. And generally this is the basic mechanisms that how the MPEG audio encoder and decoder works. So for examples, this is our audio input. Generally this is coming from PCM, pulse code modulation input, and then we need to convert from time domain signal to frequency domain signal. And then that bands come, different bands, right? And then what we do, we analyze both time, this signal, according to some psychoacoustic modeling. So this is very much philosophical things. It depends that how we hear, the various kind of experimental things happen here. So based on that modeling, we try to allocate the bit, right? As you know, the quantizations and that how many number of bits, that kind of things. So what to delete, what to not, so that kind of things we do here. And then we do some sort of encoding on that bit, maybe Huffman encoding or something others. So that encoded bit string we get. So this is the very much basic mechanism that how MPEG audio encoder and decoder works. And the decoding is the very opposite things, that you just unpacking and then reconstruction and then frequency to time conversion and so and so. So definitely there are various kind of encoder, for example MP3, and also advanced audio coding, the ASC, Windows Media Audio coding, free lossless, audio codec, in Apple lossless audio codec. There are different kind of audio codec, and mostly the difference is happen here, that each codec use different kind of psychoacoustic modeling or different kinds of coding here. Yeah, so this is the basic differences. And if you see the compression performance, MP3 compression performance is like that. Let's just telephone sound quality is bit rate is usually 8 kbps, and it is kind of one single channel, that's mono. Compression ratio is possible, 96 is to 1. So that means, for I mean, uh, I mean, compression ratio is 96 in fact. So you see very high compress we can do for telephone signal. But for cd quality signal, cd quality audio, cd quality, that bit rate is usually 112 to 128 kbps, and this is stereo signal, that is multiple channel, and the compression ratio usually 12 to 14. And there are some other FM radio, AM radio, something similar. So compression is, you see, the to preserve the high quality, for example CD sound. So compression ratio is smaller, we cannot compress a lot compared to telephone signal. So this is a general comparative scenario. So I hope that you understand it.